we start part B of module 3, problem size reduction. B.1, variable size reduction. When we reduce the problem size, sometimes we can reduce a little more, sometimes so not that much, a little bit. Variable size reduction. So we have that kind of situation. Yeah. Let's look at our example. Our problem number 9, greatest common divisor. So we're familiar with this concept, right? In high school, middle school, so you learn this concept and you learn how to find greatest common divisor of two positive integers. Yeah. So let's look at the question first. Given two non-negative integers m and n, not both 0. Here, if both 0, then the greatest common divisor is not defined. It's not defined. So that's why we do not allow both m and n to be 0. Yeah. Find their greatest common divisor, GCD of m and n. So that's the problem. All right. Before we apply the recursive algorithm on it, we like to recall our middle school procedure. Middle school procedure. That's not based on the recursive algorithm. It is based on a different method. Yeah. So let's look at that procedure first. Yeah. Step 1, find the prime factorization of m. Prime factorization. So you know that, right? 15 equals 3 times 5, right? 18 equals, let me write here, 18 equals 2 times 3 squared, and so on. So that's the prime factorization. Each factor is a prime number, but some of the prime numbers, you may need a power of that number. You may need to use the power of that number. So the prime factorization. Yeah. Step 2, find the prime factorization of n. After you have those two prime factorizations, now you can find the common prime factors. Common prime factors, right? Yeah. Then step number 4, compute the product of all the common prime factors. That's the basic procedure. It looks pretty simple, right? Yeah. Here, let me use a simple example to explain the whole procedure. Then we have discussion on it. First, let's write prime factorization for 60. 2 squared times 3 times 5. Yeah. Second, 24 in its prime factorization, 2 cubed times 3. Then our step number 3, for each prime, we look at the, common prime factors, greatest common prime factors, right? Yeah. Among these two, greatest common prime factor, 2 squared. 2 squared, right? Yeah. So each number contains this factor as its factor in that power of prime form. Power of prime form. Okay? Yeah. 2 squared. Yeah. Second one, 3. Yeah. Just 3. Yeah. But 5, it's not common, so we don't include it. Yeah. The answer is 12. All right? Then the conclusion, GCD of 60 and 24 is 12. That's our middle school method. It looks pretty simple, right? Yeah, it looks pretty simple. Yeah. All right. But, so you may want to ask the question, if we can solve the problem, just use the middle school method, why we need to do it another time using our recursive algorithm, right? You may ask this question naturally. Yeah. The answer is this. Now, this method relies on prime factorization, right? The basic operation, the prime factorization. Yeah. Now the question is, how hard is the prime factorization? Do you know how hard is the prime factorization? Okay. Here for 60, 24, that's easy, right? But for a large number, is it still easy? For a huge number, right? Can you imagine some huge number? Huge number. Here, the huge number, I can talk about an integer with 1,000 digits. How about that? How about that number? An integer with 1,000 digits. How about that? Okay, yeah. An integer with 1,000. I just write 1,000. I didn't ask for 1 million digits. So you can see, not that big, 1,000 digits. Now you're allowed to use supercomputer to do the factorization, prime factorization. You're allowed to use the most powerful computer in the world to do that prime factorization. Can you imagine how fast it is? How fast it is? Prime factorization. Many years. In order to find the answer, you need many years to do it. Is it a good method? No. Think about if we have two integers. Both integers have 1,000 digits. Another 1,000 digits. Now I ask you to do prime factorization. I ask you to find the greatest common divisor. Greatest common divisor. Can you do it? Using a supercomputer, can you do it? Right? Think about it. Can you do it? Right? Yeah. Okay? Yeah. Very, if you need to do the prime factorization, extremely slow. All right? Yeah. So we cannot do it. Yeah. So we have to use a different method. Yeah. In this video, we talk about recursive algorithm. If you use recursive algorithm, you can find GCD of those two numbers very fast. Very fast. All right? Yeah. Okay? All right. Here, let's look at a new solution. First, when we start, we want to look at our data first. First, we know GCD of m and 0 equals n. When not one of the two numbers is 0, then just the m. But here, m not equal to 0. Because based on the condition, the two given numbers, not both 0. Then we study the problem size. What is the problem size? Maximum of these two given numbers, the maximum. It's not 0, the maximum of two numbers, not 0, yeah, based on our requirement. Yeah. The question, what is the problem size? Just that. Yeah, that's easy. Yeah. But the second question is hard. How to reduce the problem size? How to reduce the problem size? We know that's the common way of thinking, right? If you can find a good way to reduce the problem size, then you're halfway to get your solution, halfway there. Okay, yeah. So let's look at that part. Yeah. Reduce the problem size. Here, we need to use a mathematical tool to do it. Some special mathematical tool to help us to reduce the problem size. That mathematical tool, everyone knows about it. Yeah, it's pretty simple one. Division algorithm. Do you know how to do division? Division algorithm, integer division. If you know how to do integer division, then you know that algorithm. Here, let me write it this way. Given two positive integers, a and a b not equal to 0. Okay, divisor cannot be 0. Then there exists unique integer q for quotient and r for remainder with 0 less than equal to r, strictly less than b, such that a equals b times q plus r. That's the division algorithm, the standard format for the division algorithm. Okay, yeah. All right. Now we need to apply it on our GCD problem. Okay, yeah. Here when we start, so we can assume m greater or equal to n, then greater than 0. If not, we can switch two numbers, so you can get that. Switch m and n, we can get that condition. Okay, yeah. So then we can apply our division formula. A for m, b for n. Then we can get a quotient and the remainder part, right? Yeah. So let's take a look. How do we do the problem size reduction? Yeah. After we use the division formula to write m-n relationship, then we need to do transform, formula transform. Yeah. Yeah. That's the key property we need to use solving this problem. Okay. All right. So through transformation, so now let's do the transformation. GCD of m comma n. Yeah. So we replace m by our division formula, nq plus r. Okay. But here you can see nq, it is a multiple of n. Multiple of n. So that is good property. We need to take advantage of it. Okay. All right. So how do we take advantage of that? That multiple thing, right? Yeah. So we do in this transformation. We look at a fraction m over n. So you can see after simplification, qn over n, cancellation q, that integer part, we take it out of the fraction. Okay, it's not part of the fraction anymore. We take it out of the fraction. Then the fraction part becomes r over n, right? R over n. Now there is a big observation we need to use. What's that big observation? Yeah. Because GCD of M and N equals the GCD of R and M. Q does not change anything of the GCD. It's an integer part. It does not impact anything on the GCD part. That's the key property we need. Okay? All right. So with that observation, yeah, so we can just cross out that Qn, right? We can cross out that Qn because no factor, nothing changed after we remove that Qn number. Yeah. So the result is we will get a smaller size GCD. GCD of N and R. We know N is greater than R, right? Yeah, greater than R. So we put the larger number as the first parameter, N and R. This way, we get size reduction. And it is a variable size reduction, right? You cannot predict how much size reduction in this way. Okay? No such prediction. Yeah, so variable size reduction. Yeah. All right, so with this new method, so you can see, use our previous example, we can do the calculation in this way. Now, GCD of 60 and 24 equals, remove the, multiple of the divisor, the maximum multiple of divisor from the first parameter. So we get the GCD of 24 and 12. Then after remove the multiple of that, maximum divisor, so get 0, 12, 0, answer is 12. Yeah, I mean the first one, because we want to use the remainder, so we can remove the multiple of that divisor part. So you can see, it is pretty easy. The most important thing using this way, we avoid prime factorization. We completely avoid prime factorization. That is a very slow process. The new process, extremely fast. Extremely fast. All right. So next, let's look at the implementation part. Okay. So for the implementation, actually, it's pretty easy. Pretty straightforward. So we can do it quickly. The algorithm we called Euclid algorithm. Euclid algorithm. So the rule is like this. GCD, based on these three cases, GCD. Okay. When y equal to 0, you just take x. But we require x not equal to 0. If both is 0, before you get into the function, you should return the, error message, right? If both is 0, data is not valid. So you should return that error message first. If you pass that step, data validation step, then we have these three cases. All right. Second, if x mod y, modulation mod y, okay? Mod y equals 0. That means x is multiple of y, then the answer is y. Okay? Two simple cases first. Then recursion, size reduction. So you can see we call another GCD, but this time it is based on the division algorithm. So y first, x mod y second. So you can see, we hope size reduced, and in this way we can keep doing the size reduction until we get the answer. How about this algorithm? How powerful it is. So think about that, how powerful it is. Yeah. All right. Because here, for the size part, we can do just some very simple adjustment. So you don't worry about if the first parameter is greater than second parameter. Even the first parameter less than second parameter, you just use one call, one iteration, you can get it right? You can get it right. Just one call. Yeah. All right. Yeah. Then the code could be written in this way. Pretty straightforward. So I think I do not even need to explain this code. You can understand the meaning immediately, right? Yeah. All right, so let me finish our B.1 video right here. Yeah.